a Young Leaders Program webinar series. Today we're joined by Dr. John Walsh, Director of Technical Water at Setco Energy Services. He will talk to us about the role of membrane and mechanical desalination in the oil and gas industry, the opportunities and the challenges. So without further ado, I'll hand over the microphone to John, and I'll see you after the talk. John?
Thank you, Asia, and it's my pleasure to be here today. I'm going to talk about desalination in the oil and gas industry. First, a little bit about myself. I recently retired from Shell after spending about 21 years as a water treatment engineer and expert at Shell. Traveled to 11 different countries and did a lot of technical services, support work to the operations. I lived in 4 different countries, being transferred with Shell, and had a what I would say is an incredibly exciting career. And then have recently joined one of the consultant and vendor companies, Setco Energy Services, where I'm now engaged in doing troubleshooting and consulting across the industry. So today I'm going to talk about desalination in the oil and gas industry. And by oil and gas, what I really mean is the exploration and production side of the industry, which would be the finding the oil, producing it, and transporting it to the refineries. And I'm not going to talk much at all about refinery operations. So why is desalination used in the exploration and production part of the oil and gas industry? What are the needs? What technologies are used? And then I'll give some examples. Now, my attempt here was to make a comprehensive list of all of the applications of desalination in the oil and gas industry. I'm going to go through some of these in detail, but let me just kind of summarize them here. For almost every offshore and remote located onshore site, there's a need for drinking water, wash water, and so on. And desalination is used to either desalinate seawater or to desalinate an aquifer, saltwater brine aquifer. In addition, water is injected into oil-bearing reservoirs to push the oil to the producing wells, and occasionally sometimes steam is used or polymer is added, and there's some interest lately in desalinating the water to enhance oil recovery, and this is referred to as low salinity water flood. In addition, I'm sure you've all heard a lot about hydraulic fracturing or fracking. Polymers are used in hydraulic fracturing operations in order to fracture the shale and to promote the placement of proppant into the fractured shale. And then finally, I'll discuss a little bit about coal seam gas, or coal bed methane as it's known in the United States, which typically requires quite a bit of water treatment and desalination. So I thought I'd start with the simplest application of them all, and that is desalination for drinking water. And this is a picture of the Mars tension leg platform in the deepwater Gulf of Mexico. And so platforms like this require drinking water, wash water, and it's generally supplied by desalination. This platform has anywhere from 120 to 160 people on board at any given time. It's a floating structure. You can see these yellow pontoons here, which extend about 80 feet into the water and which provide the buoyancy. And the platform is anchored to the sea bottom by tension legs. Each one of these pontoons has at the bottom of it has 4 tension legs. These tension legs are roughly 1 foot in diameter, 1 inch thick steel, and filled with steel reinforced concrete. And those more or less structural pipe units anchor the platform to the seabed, and they provide tension so that if the ballast water is pumped out of these pontoons. The platform lifts. If the ballast water is pumped into the pontoons, the platform goes deeper into the water. And that is controlled for storms, hurricanes, and things like that. At its peak, this platform produced 200,000 barrels of oil per day, which in today's $50 a barrel world, it would be about $10 million of revenue per day. The platform cost about $1.5 billion, so the payback was about 150 days. And a sister platform only 8 miles away is the Ursa platform, and that has a 24,000 meter cube per day sulfate rejection plant, which I'm going to talk about briefly. But desalination is used to generate drinking, wash, and cooking water. Offshore seawater is used. Relatively small units, about 100 liters per person per day, which equates to about 20 meter cube of desalination. Coarse filtration is applied, followed by fine filtration to get the silt density index down to approximately 3 or 3.5. 2 passes of reverse osmosis membranes are used, and then the water coming out of the membranes is remineralized using calcium carbonate and put into a big storage tank for use. So that's as I say, that's probably the simplest application of desalination. Is used throughout the industry. More complex application would be to enhance the oil recovery from a hydrocarbon-bearing reservoir. And typical in initial production, the reservoir will usually produce about 20 to 30% of the oil in place in the reservoir without any intervention. The operator will just drill a well, and the oil will flow of its own pressure. Secondary recovery is in application of water flood, where water is pushed down into the reservoir, and maybe an additional 10 or 30% of the oil in place will be produced. And then tertiary recovery, enhanced oil recovery, chemical flood, or steam will, in some cases, be able to produce over 90% of the oil that's in place, but of course it costs quite a bit more. So I'm going to go through some of these enhanced and improved oil recovery methods. One potential complication, especially offshore, is that the water, seawater used, contains a very high concentration of sulfate. Now, in the case where the hydrocarbon-bearing reservoir also has water containing barium, barium sulfate scaling can become a problem on the producer wells. Barium sulfate is only soluble up to about 3 milligrams per liter. And this is what I mean by this type of water flood. So we show the facilities which take seawater and processes it, reduces the particulate loading and so on, and injects it into the hydrocarbon-bearing reservoir, which pushes the oil out. Now, if the reservoir also contains water containing barium, then barium sulfate scaling will occur on the producer wells, and in that case, what the industry usually does is install desalination in the form of sulfate rejection membranes. Now, this whole technology started with the Marathon platform, the South Bray platform in the North Sea. It's kind of hard to see where it is, but you see East Bray is here and South Bray is here, and that's right in the middle between the United Kingdom and Norway. And I show this little map to give a sense of how many platforms there are, and this only shows the larger platforms. There's probably double this number in the North Sea. So as I said, high barium from reservoir water and high sulfate created a barium sulfate plugging in the wells, and that led to the development of sulfate rejection plants to solve this problem. And then this shows the development curve and implementation curve throughout the industry. Today, about 1.6 million meter cube of seawater is desalinated using sulfate rejection membranes. And then this is the SRP plant for the Ursa platform. You can see it's staged here on the ground. This was probably about 2005 or 2006, where we did a walkthrough to make sure that it was built to specifications. And this technology is an example of a very rapid uptake in the industry because of a strong need, favorable economics, and the technology was fit for purpose. This further, okay, so I'm not going to get the slide that I wanted, but this was another look at technology uptake for this technology. And one of the things that it shows as a recent implementation was in 2007, the EARTH platform started its sulfate rejection package, primarily to eliminate this barium sulfate scaling problem that I mentioned, but secondarily also to eliminate a reservoir souring problem. The sulfate is metabolized by sulfate-reducing bacteria to produce hydrogen sulfide, and hydrogen sulfide corrodes steel. It, in some cases, will make the steel crack, and then, of course, it's toxic material, and so it's desirable to eliminate it from the seawater injection. In addition to sulfate rejection plants, there are a number of technologies that help prepare the water upstream of sulfate rejection, and that would include microfiltration, ultrafiltration packages, a compact deoxygenation, which is shown here with the Liquicell membrane deoxygenation system. And membrane deoxygenation replaces a deoxygenation vacuum or gas stripping tower, which is shown here in the middle. And the membrane deoxygenation is about 1/3 the size and weight. And you saw a picture of the platforms where size and weight would be a definite concern. So then shifting gears a little bit and going from improved oil recovery or water flood and sulfate rejection onto enhanced oil recovery, there's basically three major areas of enhanced oil recovery that have to deal with water. One is steam flooding, where steam is actually injected into the ground, and something called steam-assisted gravity drainage, polymer flooding, and low salinity water flooding. I'm not going to talk extensively about polymer flood or low salinity, but I thought I'd take a few minutes to talk about steam flood because the story around steam flood sort of demonstrates how there are many constraints, project constraints, location constraints, that contribute to the selection of the type of desalination technology that would actually make the most sense. So this is a map of oil reserves throughout the world. These days, we all know that the price of oil has come down, but of course, the price of oil is cyclical. It has come down, but in the past, it will go up in the future. And a huge amount of oil is found in the Alberta oil sands, 175 billion barrels of oil, which rivals the amount of oil that is available in the Middle East. As well, there's oil sands in California and Oman. So this is a big potential reserve of oil for future production. And then what this slide shows is temperature variation of the steam as a function of different locations. And so I'll go through this in some detail. But one of the most important parameters in doing a steam flood is the temperature of the steam. Steam is injected into the ground, into the hydrocarbon-bearing reservoir to reduce the viscosity of the oil that's there. And then this is the viscosity as a function of steam pressure. This is the temperature of the steam, and then this is 1 over the square root of viscosity, which gives a measure of the permeability or the extent to which the oil will flow. So as the oil viscosity comes down, the flowability of that oil goes up. The oil viscosity comes down because of steam temperature. So you get a sense that steam temperature and the oil viscosity will control how much productivity there is from the steam flood. And this table shows the oil API, American Petroleum Institute measure of density, and actually it's an inverse measure where a high number means low viscosity and a low number means high viscosity, and then steam temperature here. And what you see is that most of these Alberta, Carmon Creek, Alberta, Cold Lake, Alberta facilities have high temperature requirements in order because of the high viscosity of the oil and other considerations. California and Oman have lower temperatures. So what we've seen in the industry is a trend toward more extensive desalination in Alberta. As temperature of the steam goes up, scaling and fouling problems become more of an issue, and that has driven the Canadian industry to implement more sophisticated steam generation methods. This slide and the next one shows once through steam generation, which is the old traditional method of producing steam. It produces a very low quality steam, only about 80% steam, 20% water. That water then has to be separated in order to produce 100% steam. And so there's a very large volume of waste. This has given way over the years, again in Alberta where higher temperatures are required and where there's greater scaling tendency, to the use of vertical falling film evaporators, in some case then followed by an OTSG, in most cases followed by a small conventional boiler, which is a much smaller unit. So I thought I'd take some time to go through mechanical vapor recompression, which is shown schematically here. Now this is true evaporation technology. Water is fed into a set of heat exchangers which capture heat from the unit. The water then goes to a de-aerator where carbon dioxide and air is purged. It enters into a brine sump, and vapor coming off this sump is compressed, which raises the pressure and the temperature. Brine is, as you can see, there's a brine recirculation pump. Brine is fed to the inside of a set of vertical tubes. This high pressure, high temperature vapor is fed to the outside of those tubes. Heat exchange occurs. Vapor is generated and captured as clean water, and then the salt water falls into this sump and then is eventually discharged, and in some cases it's solidified. So MVR, what is the operating experience? Well, vigorous flashing of brine is required to produce the required vapor flow rate, but it also produces small brine drops which must be removed to avoid the compressor fouling. Demisting filters are used for that purpose. Frothing and foaming from too high of an oil content in the feed water or poor pH control can also cause foam. Hard and soft scales can form throughout the machine and have to be treated with scale inhibitors and scale dissolvers. And then multi-effect units are also used to control scale and increase the energy efficiency. So that's what I wanted to say about steam flood. And again, the purpose of going through that in a fair amount of detail is to first demonstrate the connection between project parameters, oil characteristics, steam temperature, and then the kind of evaporation technology that might be used. Now, an interesting corollary to that is that mechanical vapor compression is also having an impact on the reuse of hydraulic fracturing flowback water. So let me explain what I mean by all of that. So in hydraulic fracturing, as I'm sure you know, a polymer is injected into the ground at very high flow rates and pressures in order to fracture the shale and open it up for oil and gas production. The hydraulic fracturing fluids are immediately flowed back to the surface, and then they must be processed. Now, one of the better ways of processing that flowback water is to reuse it, but in reusing it, problems can occur. So let me first show you what one of these sites looks like, and you've probably seen these in the media, but this would be the well, the injection well, and then what you see are all of this massive infrastructure around delivering chemicals, water, the sand that's used as a proppant, blending, frac tanks for water storage, and other trucks and tanks and pumps for pushing the water into the ground. So it's an enormous infrastructure around water. Now what this slide shows is the sensitivity of the polymers that are used to salinity. So this is low salinity, and you can see the polymer is able to achieve a high viscosity, which is desirable in order to open up the shale fractures. As salinity increases, you see the viscosity attained drops off rather quickly. A lot of times the salinity that is in the flowback water is in the range of 100 to 200 milligrams per liter, 100 to 200,000 milligrams per liter. So you see that would have a dramatic effect on polymer viscosity. One way to overcome this high salinity of the flowback water and to use it again for reuse is to use mechanical vapor recompression as a desalination option. So using the same kind of technology that we just talked about, instead of a permanent installation, modular units are constructed. A modular unit is transported on 3 flatbed trucks to a site. So this would be a site of 1, 2, 3, 4 wells in a given location. There's a water storage pond. And then this is what the mechanical vapor compression unit looks like when it's set up. This is inside of a shed. And this one is in a location, West Texas, where an outer shed is not required. And so this, and you can see that this is all skid-mounted equipment which comes on the back of a truck. It's set up, operated by 3 operators 24/7 for 2 or 3 months, and then it's dismantled from this well site after all of the hydraulic fracturing is accomplished, and then moved on to another site. So I thought that it would be interesting to show what the mechanical vapor, the impact of mechanical vapor recompression is, both on steam flooding in Canada, where high temperature steam is required to mobilize the heavy oil, as well as in hydraulic fracturing, which is implemented throughout the U.S. in Pennsylvania, Nebraska, North Dakota, and West Texas. And then as the final application, I thought it would be interesting to show, coming back to membrane filtration, the coal seam gas or coal bed methane fields require extensive dewatering at the very initial stage of production, because these coal seams are full of water, they're saturated with water, and the water has to be pumped out in many cases in order to start the flow of hydrocarbons to the surface. Now that produces a large volume of relative low salinity in the range of 7 to maybe 12,000 milligrams per liter of salinity. And in many cases, the salinity is just too high to discharge into rivers, lakes, and agricultural area. So the water is desalinated using initially an ion exchange resin followed by reverse osmosis. The permeate then can be used for irrigation and surface disposal into rivers and lakes. It's relatively clean drinking water. And then the brine that's produced, the concentrated brine, is usually evaporated, and the solid is sent to a regulated waste facility. So I hope I've given a sense of both the enormous breadth of application of desalination in the oil and gas exploration production industry, as well as provided some depth in a couple of the technologies. We talked about desalination for drinking water, both offshore and in the desert, improved oil recovery through water flooding and the problem of barium sulfate scaling, and as well as souring. And we talked about temperature, steam temperature in the heavy oils in Alberta, Canada, where mechanical vapor recompression is used. And we talked about mechanical vapor recompression for hydraulic fracturing in using mobile units, and then coming back to membrane for surface discharge of coal seam methane. And so that's basically all that I wanted to say, and I'd open the audience to questions.
Thank you very much for your talk, John. Very interesting. I'm gonna just take a look at the comment section to see if there are any questions from the audience. In the meantime, there is one question for you. The question is, what are the typical silica concentrations in the Alberta oil sands?
Yeah, go ahead.
John, can I just Can we see you again? I have your presentation still up.
How's that?
Perfect. Yep.
Okay.
Thank you very much.
Yeah. So, okay, so offhand, I would say in the range of probably 200 to 400 milligrams per liter, which is another factor driving the industry to the use of MVR, because in the OTSG approach, silica concentrations approach saturation and cause many scaling problems. In the evaporator application, silica is still a problem, but can be controlled through the use of chemicals. And yeah, and then in California and Oman, silica levels are somewhat lower and controlled by steam application of steam temperature. In fact, that's one of the reasons why steam temperature in California is maintained relatively low, is to prevent the whole silica, first of all, dissolving the silica and then preventing the silica scale problem from occurring. Did that answer make any sense?
Absolutely. Which brings me to the second part of the question. How much silica can the mechanical vapor recompression tolerate before scaling?
That depends on the chemical used. It depends on the both and silica inhibitors, as well as the application of seeded slurry systems. In a seeded slurry system, the objective is to precipitate magnesium, calcium, and some iron simultaneously. Sorry, I'm getting some of these concepts mixed up. In order to control the silica.
Yeah. Okay, that's very interesting. I want to ask a question from a very different topic. Produced water treatment from conventional or non-conventional oil fields. There's a big buzz for the use of low-pressure membrane technology for produced water treatment. And well, at least from a research point of view, there's a huge tendency towards ceramic membranes. Do you see at all a role for polymeric low-pressure membranes in produced water treatment applications?
Yeah, and I think probably the most likely entry point will be in the hydraulic fracture flowback operations. One of the characteristics of membrane separation is the permeability and the flux rate. The LMH, the liters per meter squared per hour, tends to be in the range of several hundred to maybe 1,000, which is reasonable to consider onshore application for something like hydraulic fracturing flowback, where rates of maybe a barrel a minute to 7 barrels a minute are acceptable. It's unlikely to see that technology be applied offshore. LMH requirements offshore tend to be in the several thousands to 10 or 20,000 LMH, just because of the lack of weight and space available to deploy equipment. But there have been some interesting applications and pilot studies of membranes, particularly PVDF seems to be particularly successful for membrane application in hydraulic fracturing applications. Typically the water, depending on the micron size, but the water coming out of the membrane is crystal clear with almost all of the total suspended solids removed. And this is keeping in mind that there may be 2,000 to 4,000 milligrams per liter of total suspended solids. So for water to come out of the membranes almost crystal clear is quite an achievement. But flux rates are relatively low, in the range of maybe tens to 100 LMH.
And what is the lifetime of those membranes?
Still under investigation, but in many cases weeks to months, which is not a significant handicap in application hydraulic fracturing because oftentimes all you need to do is apply the separation technology to a cluster of wells, maybe 4 or 6 or 8 wells over a period of a few months, and then after that, then the membranes can either be replaced or can be chemically cleaned, vigorously chemically cleaned. So it's not necessarily such a handicap. We are looking forward to developments in ceramic membranes. Again, the ceramic membrane installations that I've seen are very successful in cleaning up the water, but require a relatively high recycle ratio, almost a 10-to-1 ratio of feed to permeate, and that requires a large system to recycle all that water and relatively large pumps.
John, you mentioned that the water coming out of these PVDF membrane systems is crystal clear, and I just want to ask a question about the rejection of naphthenic acids. Could you say something about rejection rates?
Yeah, well, naphthenic acids depend very strongly on the pH. If the pH is high, and by high I mean anywhere from 5 and above, the naphthenic acids are in the sodium or ionic form, and as such, then they're dissolved and they're not going to be rejected by either the polymeric or the ceramic membranes. At lower pHs, the acids are then protonated. They're still very polar, but they're not ionic. And it is possible, if you use the right flocculation chemistries, to remove a good fraction of the naphthenic acids at the lower pHs. And if that's your objective, then it is definitely possible to do that. Naphthenic acids, it depends on which location, but naphthenic acids can be in a concentration range as high as several hundred milligrams per liter to, in some cases, 1,000 or more. Is there more to the question?
Absolutely, yeah. Thank you so much for that.
Okay.
I'm going to take another look to the to see if any of the viewers who are watching this webinar right now have any questions. You can post your questions right now on the YouTube comment sections. I'm going to get back to you. So is it fair to say that the hydraulic performance of polymeric membranes is not much of a concern, rather the rejection capacity?
Yeah, it depends. Are you referring to polymeric for desalination or for total suspended solids removal?
Well, in this case, for the flowback of produced water treatment from hydraulic fracturing, I would say.
Yeah, pressure requirements are usually not a limitation. These facilities, as you know, as I showed the layout of all those trucks and tanks and so on like that, typically have plenty of energy available, whether that's from the actual gas that's being produced in neighboring wells or diesel that's trucked into a location. But usually pumping requirements, energy, and so on is usually not a significant constraint in those operations. Now, and offshore, where membranes are used for desalination, they're also used onshore as well, but in the offshore application, interestingly enough, energy is usually not a constraint either. You find that almost no installations of desalination membranes offshore are using these energy recovery devices, whereas onshore for drinking water, they almost all use energy recovery. But in the offshore economics, the added weight and space and complexity of adding energy recovery devices does not provide sufficient incentive for their use. And that's in part because energy is so plentiful at these locations.
Absolutely. So, John, I think it's been a very comprehensive presentation. I enjoyed a lot. I hope it gives our viewers ideas. My ideas have changed. I have to refine my research plan a bit based on what I've heard from you today. And we would like to thank you very much from the IDA YLP for your time. And if there are no further notes or comments, I would like to thank you very much and close the session.
Great. Thanks, Asiya.
Thanks very much, John.